Okay, welcome to note set number 4, where we'll be talking about difference equations. Still somewhat of a review, although a few of the things will be a little new perspective. We'll hit a little more on block diagrams that we didn't really talk about too much in the signals and systems course. We're in section 2.4 of Proakis and Monolakis' textbook. So if you remember, we were talking about convolution and saw that it was one of our methods that allows us to figure out the output of a system. And every one of the methods that we have, as students, you think of them as a way to answer a question on an exam. How do I, the professor's going to ask me, here's a system, here's an input, find the output. But in reality, engineers don't really do convolution or don't really solve for specific outputs all that often. Professors ask you to do that to make sure that you understand the mechanism. We really use it as a way of understanding how things really are going to work and how we can think about implementing systems and things like that. So that leads us to the question, could we use this idea of convolution to actually implement, and by implement we mean really build a discrete time system? And so let's give that a little bit of thought here. So suppose we have a scenario, practical scenario, with a causal system. So if we're dealing with time systems, causal systems are the only things that we can really implement. And we're going to have an input that starts at some point, and we might as well call that input time n equal to 0. I mean, that's what engineers are doing, do when we talk about n equal to 0. It's our choice to say this is the time point where things are going to start. So if we have an IIR system, so infinitely long impulse response, our convolution for this scenario ends up looking something like this, and the key for this is that the upper limit on the summation is the current time at which we're trying to find the output. So the output at the instant n, to compute that, we would have to sum from I equals 0 all the way up to n. So we can see that we are constantly adding in one additional term. As n gets bigger, we're adding in one more term into the sum, to include farther and farther out into the impulse response. And so to actually directly use convolution to implement this, we would have some problems because for an IIR system, as we went further and further along in computing our output, we would have a sum that grows longer and longer and longer, and that becomes a problem. But on the other hand, if we have an FIR system, a finite duration impulse response, and suppose we have one of order m, then we will have something that will look like this. We have a summation whose length doesn't grow. Notice that regardless of the value of n, we always have just m terms in our sum, and so the computational complexity is just fixed, and we would need only m multiplications and m minus 1 additions to do that. So we have m terms in the sum that each require multiplication of an h term times an x term, so that's the m multiplications. And then we have m things to add together, so that requires m minus 1 additions. And we can visualize this process, so this FIR convolution can be thought of in terms of this block diagram that's shown at the bottom here. Let me get rid of some of this red stuff up at the top here. Didn't happen. There we go. And so if we look at this diagram on the bottom, remember each one of these Z inverse boxes is just a delay box. So and initially every one of those delay boxes, or we can also view it as just a memory location that holds something, each one of those will be loaded with 0. Those are the 0 initial conditions. And so at time equal to 0, we would have x of 0 here at the input, and we would calculate our output would be x of 0 times h0, and it would go into this big sum here. All these other values here would be zeros, so we would have h of 0 times x of 0 plus a whole bunch of zeros, and that would give us y of 0. And so if you go back and look at what this is going to look like for what that sum would look like for n equal to 0, recognizing that any x of negative indexes would be 0, because we're assuming our signal starts at n equal to 0, you can see that that actually computes y of 0. And then similarly, if we then think about what happens on the next clock cycle, so we have to think about this being clocked. So on the next clock cycle, everything gets shifted through these memory locations. So we would have we had x of 0 there. We're now going to have instead x of 0 gets shifted over to here, and x of 1 is there. And so you can see that now n is equal to 1, and n minus 1 is equal to 0. And so I'm not saying these are the values, I'm saying these are the indices. All the other x values would be 0 at that point. And so we would get x of 1. Let's see if I can do this tricky thing. Let's see, can I do this? I don't know how to do this, sorry. Oh, okay, I got it. So we would have an x of 1 getting multiplied by an h of 0 and going to the sum. We would have an x of 0 multiplied by an h1 going into the sum, and then all of these terms would all be 0. All the other things coming in would be zeros. So we get the y of 1 output also follows exactly what this equation shows us. And so for each clock input, this stream of inputs gets shifted in further and further and further. And so what we're seeing here is, as shown in the diagram here, what we're seeing is at the nth position. So after we've clocked in n samples, we've got x of n here, whatever that is, x of n minus 1 here, x of n minus 2 here, and so on. X of n gets multiplied by h of 0, so you can see that x of n would be for the case of I equal to 0, so we have x of n times h of 0. Then this product here, x of n minus 1 times h of 1, is for the I equal to 1 case. This is the I equal to 2, I equal to 3, all the way down to the I equal to m minus 1. So you can see that this block diagram does indeed implement what this little convolution, FIR convolution equation actually says it does. And so we have a nice way of visualizing FIR convolution. And if you think back to how you did graphical convolution back-end signals and systems, think about this. What we've got is H not flipped because it's in ascending order of indices, and we've got X flipped, and we are constantly moving X into the flipped version of X. We're moving it into the H value. So this is literally doing what we do when we do graphical convolution. So I'd encourage you to go back and review that graphical convolution and connect it to this idea of this simple block diagram for an FIR filter. Later we'll see block diagrams that we can build for certain types of IIR filters, and we'll be using feedback. So in that context, let me just make one last comment here before we head off onto the next slide. When looking at a block diagram like this one, we say that we have feed forward. Everything is going forward. So an FIR filter like this is built with feed forward parts of the block diagram. Later we will see portions of Y getting fed back into these delays, and that will give us a more general IIR system. Okay, let's right here. We'll talk about, in general, IIR systems and recursion and difference equations in general. So we've seen that even though convolution can theoretically describe either an FIR system or an IIR system, to actually implement the system in our computers, convolution really only tells us how to handle the the FIR case. Now, as I just mentioned, for some IIR systems, not all, but for some, and usually those are the ones that are of interest to us, we can actually implement this in a recursive form. And so the recursive form ties into what I was just talking about with feedback. So let's look at a motivating example here for this. And so suppose we want a system that just accumulates our input, just keeps adding it up. And so we could write that with an equation that looks like this. The output at time n is just the accumulation or sum of x of 0 plus x of 1 plus x of 2 all the way up to x of n. And so that's one way to write it. And if you look carefully at this, you can actually interpret this as a convolution with an impulse response that is just the unit step. So I'd encourage you to try to think about that and write that out as an explicit convolution form, and then boil it down to look like this equation using properties of the unit step function. But we know that since that is an IIR impulse response, we know that that is not really a good way for us to implement it in general in our system. But for this particular one, we can play a little trick. And if we think about if we've accumulated up to, say, time n-1, that would give us this term right here. So that's our output at n-1. Now, if we want to create the next output, instead of just going back and accumulating all those numbers back up again, well, we've already accumulated up to n-1. We just need to add in one more term, which would be the x of n term. And when we add that in, we get y of n. Okay, so given that, if we look at that carefully, what we can do is say, well, I've got y of n is equal to y of n-1 plus x of n. So we can rewrite this way, and we now get a recursive difference equation where some current y of n is equal to some function of past outputs. In this case, it's just one single past output, y of n minus 1, plus, in general, the current input plus some number of past input samples. And in this case, it's just the current input. Now we've recast what looked like something that we couldn't really implement. We've recast it in a way that we can implement. We just need to have saved some past outputs. So to compute the current output, we need a past output sample and the current input sample for this particular system. And that leads us to the difference equation. We've looked at this difference equation earlier, and we're just restating it here. And if we think about this linear constant coefficient difference equation that we have here, and then we can rewrite it in a more general form. And the little dotted red ovals there on the bottom are just showing that we've taken care to write the y of n term separately. That's why this sum starts at k equal to 1. Whereas on the right hand side we start the sum at k equal to 0 because we don't have any need to separate the x of n term separately. So we've got that, and let me just get rid of all that crap for now. All right, so we've got that, and if we swing this term over to the other side, we get a negative sign out in front, and so that's all good. And so this is just a recursive form, and we can see that we have a fixed number of a fixed and finite amount of computations that we have to do for each output sample. So we would need to compute y of n for a given n, we would need to do n multiplies and n minus 1 additions to compute this first term, and then an additional m multiplies, actually m plus 1 multiplies, and m additions to compute the second term, and then one more addition to add the two terms together. So clearly we can implement any linear constant coefficient difference equation that looks like this thing up at the top. We can implement it in a recursive form where there's a fixed and finite amount of computation that we have to do. And so that's very, very nice. So a system like this that has these, well, let me clear off some of this stuff here. So a system that looks like this, we can see that we do have some feedback going on here, right? Here's the feedback. We've got terms that are past outputs that are being fed back to create the current output. So anything that has a recursive form like that fundamentally has feedback, and also fundamentally will be, in general, an IIR filter. There may be a few special cases where you can trump up the AKs and the BKs so that this thing really ends up having a finite duration impulse response. But in general, this is the form for an IIR system. And we'll dig into these issues quite a bit as we go into the later parts of the course. So just to get a little feeling for how this works and to see some of the characteristics of it, let's just look at a very simple recursive difference equation, what would be called a first order difference equation, because the difference between the current sample and the farthest back history of the output sets the order. And so since the difference between n and n minus 1 is just 1, this would be a first order difference equation. We're going to assume that our input is non-zero only for n greater than or equal to 0. So if we look at this equation and we say, all right, we want to start computing at n equal to 0 because that's when our input starts, we need to know y of minus 1, because if we put in 0 for n there, we're going to have y of 0 minus 1. And so we'll need to know what y of minus 1 is. And so that is actually what we would call the initial condition that we need in order to recursively solve this. So if we assume that we either know what that is, or sometimes we assume that it's 0, in which case we would be finding only the 0 state solution. But let's assume that there is some initial condition, and let's not worry about why there might be one, but there might be something there for some reason. And let's say that we know what it is. So we would have that y of 0 then is just a times y of minus 1 plus x of 0. And we could compute what that is. All right, given that we've just computed that, we then go on and we say, well, y of 1 is going to be a times y of 0 plus x of 1. But we have y of 0 already, so we can just plug that in. Let me abandon that attempt and just try to get rid of it all using my newly found trick. So we plug that in. So we plug this in for y of 0, multiply through by the a, and so you can see that we get an a times an a, and that gives us this a squared. We get an a times the x0, and that gives us this term. So all of that stuff we can see is actually coming to bear. And if we work all that out, we end up getting something that looks like this for y of 1. And we can keep repeating that. Now when we get to find y of 2, we're going to have a times y of 1. So all of this stuff gets multiplied by a, and we can see that we'll get a cubed and an a squared and an a term, and then we add in the x2 that was there, and so on and so on. And we can identify a structure here, and we can write it out. And we can see that we always have, let me get rid of a bunch of that stuff there. If we track this through, we can see that we always have an a to some power times y to the minus 1. And in fact, that power is always 1 more than n. So we have n equal to 1, and we have a squared. So we're going to have a to the n plus 1 times our initial condition. And then the other stuff we see ends up being a summation over x of 0, x of 1, x of 2, and so on. And we can see that the power of a and the index of x always adds to 2. And so if we think about that, this will be the expression that we'll have. A to the k times x of n minus k. So the power plus the index always adds to n in this case. So it added to 2 here because of we were at the y of 2 up there. So in general, it will always add to n. I think I may have just slightly misspoke earlier, but I think you get the idea. In fact, we can deduce what this thing looks like, and we can see that we end up with 2 different parts. One part here depends only on the initial condition, and the other part depends only on the input. And so that's nice. We can separate this into 2 different parts. And if you remember back to the end of our signals and systems class, we saw that we had things called the 0 input response and the 0 state response. So again, I'm just trying to force your brain back to think about those things that you may have seen a while ago, maybe not that long ago. I don't remember. I don't know when you've taken signals and systems. That's the downside of this online method, but presumably you've had it. Chances are you had it online from me. And so now you're seeing that we're revisiting that. So we have our 0 input response. So that if the input is 0, then this term goes away and we're left with just this part, which is what we call the 0 input part. And conversely, if we, to get the 0 state part, we set the state to 0, so that part goes away and we're left with this part, which is what we call the 0 state response. So the 0 state response is what we get when the state is 0. Just another name, state is just another name for initial condition, and vice versa. So that's the structure that we get, and we could deduce this for this simple case, but we know that we can do Z-transform solutions for this. We'll revisit those briefly in one of our later note sets, but you should go back and realign your mind with those ideas. Okay, moving on to the next slide. I've just repeated what we had on the bottom there, and just adding a bunch of terminology here. So a lot of it is just saying the things that I just said. So the 0 input response is what we get when the input is 0 and it's the response only to the initial conditions. And notice that it's an exponential response here, and we've already seen from our Z-transform studies that exponentials show up in a natural way, and so that's no surprise. And then the other term, 0 state response, is the response to the input when the ICs are 0. And if we look carefully at this, we can see that this is indeed a convolution. So we've already seen that the convolution solves the 0 state part of the response. And we can actually deduce from this what the impulse response is for this particular system. So if we look carefully at this, we can deduce that the impulse response is going to be a to the n u of n. Now, just a few points to bring out here. Remember, we talked about stability of systems, and we said that the absolute value of, if we take the absolute value of the impulse samples and add them all up, if that sum is less than infinity, then the system is Bibo stable. So look at this a to the n. And remember, we talked about how if the magnitude of A is less than 1, then this thing will decay. So we have to have a decaying impulse response in order for that sum to end up being less than infinity. And it can't just be any old decay. It has to be a fast enough decay. And this turns out that if the magnitude of A is less than 1, we can show that that will indeed sum to something less than infinity. And so this system will be stable if the magnitude of A is less than 1. If the magnitude of A is greater than 1, this system's output will grow without bound, and the system will be unstable. And it's pretty easy to see that if we just look up here, even just at this term. This term's going to keep growing without bound if A has a magnitude greater than 1. So all these things fit together, and you can tie that back together with things you learned in signals and systems about poles being inside the unit circle in order for the system to be stable. So A, for a first order system, A sets the one and only pole of this system, and with the magnitude of A being less than 1 would put that pole inside the unit circle. So all these pieces of the puzzle hopefully fitting back together so that you can kind of get a feeling for how all of this works. All right, we're going to go on to the next one here. Slide 7 of 8 of our slides in this note set, just showing that we can also verify that this difference equation does indeed have this impulse response. So we kind of deduced that by looking at that zero state response and interpreting it as a convolution and then puzzling out what the impulse response would have to be for that to be a legitimate convolution. But we can also just say, hey, we have a difference equation that describes this linear time invariant system. We can literally find the impulse response. Put in a delta function. Put in delta of n and see what comes out. And remember that the impulse response is always under zero state conditions. So the impulse response is the zero state response to the impulse function applied at the input. So if we just recurse this, starting with an initial condition that's equal to 0, so we'll have a times 0, and then since we're putting in the delta function, x of 0 is equal to 1, and so we get a 1 out. Then recursing this, we go to h of 1, so we have a times h of 0. Well, h of 0 was 1, so we plug that in. And now x of 1, since the input is a delta function, x of delta of 1 is 0, so we have a times 1 plus 0 gives us a. Now we just keep doing this. We have a times h of 1. Well, h of 1 was a, so we have a times a. And remember, all of these x's from this point on are going to be 0 because it's the impulse as the input. So we're just going to keep getting each previous output gets multiplied by a. So we had 1, then 1 times a, then a times a, gives us a squared, then a times a squared gives us a cubed, and ultimately for the nth one, notice that h of 3 gives us a 3, h of 2 gives us a 2, and we can deduce that h of n will be a to the n u of n. So that's exactly what we deduced on the previous slide. And you can always do that for any, any difference equation. The issue is whether you'll be able to deduce what the closed form is for it. So by closed form, I mean we can write down an expression that doesn't have any infinite sums or even finite sums or anything like that. It's just a functional expression. And so sometimes we can deduce that and sometimes we can't. But we still do know that it's very easy to find h of z. You did this in Signals and Systems. From the difference equation, we can go to h of z very, very easily. We'll hit on this again in maybe the next set of slides or very soon. You can get h of z, and then you can do an inverse z transform on h of z to get little h of n. And so that's how we would do that in general. And I would encourage you to try that approach for this difference equation to refresh your memory on a very simple one. In fact, I think we did that in the notes for Signals and Systems. So give that a try and see if you can verify that a second way, actually a third way, that this is the impulse response of this system. Okay, one more slide to go here, and we just want to hit the big picture here. So we've got our systems being described by linear constant coefficient difference equations, and we end up recognizing that our solution can be broken down into two parts. The zero input part, which is due to the initial conditions, and the zero state part, which is due only to the input. And so the zero state part we've seen already can be solved via convolution, convolving the impulse response and the input. And in Signals and Systems we saw a few other ways that we can solve that using DTFT, for example, or Z transform. The zero input part, well, drawing from your experience with differential equations, there is a way to find roots of a characteristic polynomial and so forth. In general, we would use these Z transform methods, which you saw at the end of Signals and Systems, and we'll revisit again here in Chapter 3 before we get into more of the meat of this course. So again, I strongly believe that going back and revisiting, I could start right immediately with new stuff here, but I never like to do that because overlapping the end of one course with the beginning of another course, I feel is the best way to ensure a seamless transition, as well as just reiterate the fundamentals and the basics so that you can more solidly move into the new stuff. So we'll stop there, and I'll see you in the next set of notes.